in grade 11, we added two types of vectors. They were angles at right angles to each other, and we used Pythagoras, right? Because it's a right triangle. And how many people used Pythagoras when they were not a right triangle in their test? About 20, 30%, something like that. Hopefully none of you guys, right? So you would have used like c squared equals a squared plus b squared, or some sort of, version of that. When the vectors were at right angles to each, not at right angles to each other, you had to use a scale drawing, right? You had to actually, that actually almost looks like a right triangle, doesn't it? You had to actually get a ruler and a protractor out, right? Don't have to do that anymore. I'm going to show you the real way to do it. Okay, so a little demonstration here, so to get you started. So here I've got vectors A and B, okay? And if I add them together, oh no, I always forget how this works here. Oh, maybe I just do this. All right, here we go. Okay, so then we're going to take vector A, and we're going to take vector B, and we're going to add them tip to tail. Remember that? Okay, but if we do it by components, you take this one here, that x, and you take the x of the green one, which I will do in, well, blue, I guess. Look where it ends up. And if I take the y of the red one and the y of the green one, which is from there to there, look where it ends up. Do you think we can use that? I thought there was more to this one. Do you remember components? Hello? Yes? You should maybe jot these down. Here's a good sort of refresher. So if this angle here is the theta, I better pause, eh? So if that angle there is theta, what is the formula for FAX, the side that is adjacent to the angle? It would be FA cos theta, right? Cosine being adjacent to, remember that stuff? Now some of you, when I did this in grade 11, I've sort of changed my routine a little bit. Some of you I called this, I didn't call it FAX, I called it FX or FH. And I've gotten away from that now, so I'm calling it FAX, which is the x component of the applied force, which would be the place that you sort of first saw it. Okay, but this is true for forces or velocity vectors, right? So if FAX is FA cos theta, what then is FAY? It would be FA sine theta. Right? Those are things you need to know. Are those reasonably familiar? Yeah? Austin? Okay. Okay, so we're going to use this idea in adding. So here's how this works here. So I'm going to take a version of A. Let's start from right there. And I'm going to add, how do we add vectors again? Tip to tail. Right? And so the resultant would be from where you start to where you end, right? Okay, now if I show the components, if I take vector A, the x component, and the x component of B, place them all tip to tail, and the x component of C. Now, where should I place this one? Like this?
No,
like that. Right? Okay, because again, it would be tip to tail, right? See how those are tip to tail? So this is tip to tail too. It just goes sort of backwards, right? Which means the overall resultant, and I'll put it in black, the overall resultant is that one there, right? We would call that Rx, x component of the resultant. And now let's do the same thing with the y's. Separately, there's AY, there's BY, place them tip to tail, and CY there, which makes the overall resultant Y, RY equal to that, right? And now here's the trick. You take Rx And you take ry and you add them tip to tail, and because they're x and y, they're automatically 90 degrees, which means you can use Pythagoras, and guess where you end up? Pretty close to the result. You're supposed to. It's because of some poor drawing on my part. Okay? So I just sort of showed you how to do it. I didn't sort of give you I gave you the steps, I gave you sort of the general idea. We found the x components, and then we added them together. We found the y components, we added them together, and then we added the rx and the, I guess I never labeled this one, the ry together by Pythagoras, and we get our result. So let me show you how to exactly do that. Here's an example. I'll pause there for a second and let you jot that down. We're going to add these three displacement vectors together. Okay, so we have three displacement vectors, and I've sort of selected them for a couple of different reasons. We have the first one, which is 0.5 kilometers at north 20 east. Now, I'm hoping you all remember sort of these directional kind of notations. So north 20 east means look to the north and go 20 degrees to the east. Remember that stuff? Okay, and it's 0.5 kilometers. And then D2 is 0.3 kilometers straight west, obvious. And then 0.8 kilometers at west, 50 south. So west, looking west, 50 towards the south. So we're going to add these three. Now, if we were going to do them the old grade 11 way, we'd go tip to tail and get out a ruler or protractor, and we'd get pretty close, right? Let's do it by components, okay? So let's find the components of D1. So I've redrawn D1. You probably don't need to do that because it's right there on your page, right? So what you should do, though, is you should complete the components. Right? This is the first one. So you should call this one D1y and call this one D1x. And I would suggest, I don't know how you drew these guys. Did you draw these sort of across like that, left to right? Okay, so then I would suggest you put what this stuff is over here, put it sort of like underneath. Right? So that it sort of matches. Okay, so what would be D1x? Opposite. D1x is going to be opposite, so we're going to use the sign. So it would be opposite. It would be 0.5 times the sine of 20. Which is 0.17. And that's to the right, so it's going to be positive. D1x, the x component of D1, displacement 1. So D1y would be 0.5 cos 20. Are these always going to be the same, just one sine and one's cos? Yep. That's going to give you 0.47. Also positive because it's up. Good, yeah. Okay, so now we're going to do the same thing for D2, but D2 was straight left, right? I don't think I got anything else here, no. Okay, so there's D2. Again, you don't need to draw it, just draw this, just write this part underneath it. So D2 is straight left, so D2x is simply going to be minus 0.3, because that's the value of it, right? It's all x. Is there a y? There is no y. So now we're going to have to do the last one. There it is there. Again, you shouldn't have to redraw, just do it underneath. I didn't label this. D3x, D3y. Now this time, the x is adjacent, so it's going to be cosine. So the value is 0.8 cosine 50, adjacent cosine. Does your calculator give you the negative in this negative 0.51? It does not. Why is it negative? Because the x is to the left. Is that important? Super important. You have to get that right. Okay? And you'll also notice that the y here is down, so it's also going to be negative, right? 0.8 sine 50 down minus 0.61. Okay, now way back here, what were the three steps? I found the components, then I placed them tip to tail. So mathematically, how do we place them tip to tail? How do we add them? Well, because they're all x, you simply, oops, didn't go far enough, right? You simply add the x's together. Okay, so Rx, x component of the resultant, is equal to d1x plus d2x plus d3x, and if you've got a d4, you gotta add that in too. You literally add the x components together. They're just regular numbers, plus and minus numbers, so you can just sort of add them. So in this case here, 0.17 plus minus 0.3 plus a minus 0.51. And you get an answer like that. And now what do you do with the y's? Back to the same thing, right? Just add the y's together. Ry is d1y plus d2y plus d3y. I'm going to leave that covered up while you guys write down the answer. And you should get an Ry of minus 0.14. Now, it's not 100% important or vital that you draw a picture here, but do you get the sense that you should draw those out to sort of get a visual idea of what's going on? Yeah, you probably should. Until you've done some practice ones for sure, right? So draw that out. Rx is minus 0.64 to the left. Ry is minus 0.14 down. What's the next step? Let's go back. What did we do? Put them tip to tail. I drew them here. Then how am I going to find this red one? So right angle, so you're going to use Pythagoras to do that, right? So now we're going to take this and we're going to solve for the hypotenuse R, resultant. How are we going to do that? Good old Pythagoras. There, I just redrew it for you. Right? That's the one you just redrew. And you're simply going to do this. R squared is Rx squared plus Ry squared. Minus 0.64 squared plus minus 0.14 squared. And you should get 0.66. Which is about right. That's 0.64, that's 0.14. It's going to be bigger than both of them. This is relatively small compared to that, so 0.66 seems about right. Am I done?
No.
How come, Josh? Because you got to find the angle, the direction, right? And is it always going to be tan? Yeah, because you're always going to have an opposite and adjacent. You are always going to have a right triangle here. Always. That's the whole idea. So you're going to find this angle here where you start, opposite, adjacent, right? So second function tan, 0.14. Do I need the negatives in there? The negatives are just there for direction. Now you've just got a regular triangle. You should get 12 degrees. And with that 12 degrees, you also need the actual directions. So that's going to be from there. That's going to be west 12 south. So your answer is 0.66 kilometers at west 12 degrees south. How accurate is this compared to ruler or protractor? Far more accurate. Provided you do it right, of course, I guess. All right? Do you wish I'd shown you this in grade 11? Do you feel superior to those grade 11s now? Did you know how to do this? You can sort of look down your nose at them, kind of mock them a little bit. Don't do that, but yeah, you do that anyway. Okay, you can feel a little bit superior. Okay, now whether this is for everyone or not, I don't know, but here's the steps. Your choice whether you want to write this down or not. What were the steps? What's the first thing we did? We found all the x and y components, right? That's the first thing we did. After we found all the x and y components, what did we do? Did we not add all the x components together? Right?
We added all the y ones.
Attaboy. We added all the y. And after that, made a right triangle. Used Pythagoras. Oh, I got the x and the x components. Got to proofread my notes. Use Pythagoras to add the x and y components. And find the angle. Lots of steps, but relatively straightforward. Just sort of work, not too much thinking work, right? I'll tell you the most common mistakes are way back here. People get the sine and the cos mixed up. Okay? So if you label things nice and I can see what you're doing, lots of people get it wrong. We have to get 5.5 out of 6 because they make a mistake here with the sine and the cos. So show your work, label things, and you should be just fine. Should we try one? Why don't you try that one? That'll take. Okay, I'm seeing sort of similar problems sort of around things that I've all seen before. Okay, so I suggest drawing the vectors down the left-hand side, putting your x as sort of in the middle column and your y's kind of in the right-hand column. Works good for me. Okay, so 2.3 kilometers per hour at south 40 east. So south 40 east. So looking south, we're going to go 40 east. Right, so now complete that component. So this is going to be 2.3. We'll call this one V1Y and V1X. Right? And this angle here is 40 degrees. I like doing the x's first, just no reason, just convention. So the x here is opposite, right? It's the opposite side. Opposite is automatically sine. So V1x is going to be V1 sine theta. And whether or not you write that down is up to you. I just did it sort of by habit there. So that would be 2.3 times the sine of 40, which is 1.47, 1.48. 1.48, and it's to the right, so it's positive. And then I like to do the y beside that. So v1y is going to be v1 cos theta. Always the opposite trig function. This is adjacent. There's the angle there. It's adjacent. It's beside it. Adjacent is cosine. So this is going to be 2.3 cos 40. (1.76), and that is down, so it's going to be negative 1.76. Everybody with me? Okay, so now the next one, 1.8 kilometers per hour straight north. Right? So V1, now there is no x here, is there? There's no left or right. V2, not V1. V2x is going to be 0. And V2y is going to be straight up positive 1.8. Okay, and then the last one, 2.1, east 50 north. East, actually, you can draw the whole thing. East 50 north, so east and north, right? With the angle being 50. .1. This is going to be V3x, V3y. V3x is equal to V3. Now the x here is beside it, so that's the cosine. So that's going to be 2.1 times the cosine of 50. .35 positive, so to the right. V3y is going to be V3 sine 50, 2.1 sine 50. .61, and that is up, so positive. Okay, so I've done the components. Now to add the x's, all I ever do is I just kind of do this. And you're just adding that column of numbers, right? So, and it's probably a good idea to show it. More than anything, if you make a mistake, then I can see you know what you're doing. So that would be 1.48 plus 0 plus 1.35. .83. RY, again, add that column of numbers, minus 1.76 plus 1.8 minus 1.61. Oops. I get negative 1.57. Oh yeah, it shouldn't be counting, you're right. .76. .65. I guess there's a good reason to show your work. I would see what mistake you made, and then I would, in that kind of situation, I might not even deduct, depending on my mood for the day. Right? That's just, I mean, if you know exactly what you're doing, you didn't make a sine cosine mistake, you just sort of, I looked at that and saw that half an equal sign there and said, oh, it's negative, I guess. Right? So, in a case like that, you might get away with that mistake. And then draw your picture together, right? So 2.83 is going to be our x. 2.83, and our y is going to be 1.65. There's our resultant. R squared is going to be 1.65 squared plus 2.83 squared. R equals, you should be able to do that sort of straight on your calculator. Shouldn't have to write it all down. I get 3.28. I don't even know what this is. Kilometers? Kilometers per hour. And then you got to go find your angle, right? Inverse tan, opposite, adjacent, opposite 1.65, adjacent 2.83. I get 30 degrees. So that's going to be east, 30 north. How much would something like this be worth on a test situation, do you think? Lots? One for the angle, one for that. I probably wouldn't give a mark for that. Right? Probably one each there, that's 4. And in this situation here, maybe 1.5, maybe 3 for all this up here. Because there's 3 of them, right? Like half, 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 half. You're kind of doing the same thing over and over again. 3, 4, 5, 6, maybe 6 or 7. Relatively easy marks to get though, right? If you know what you're doing. Any last minute questions there?
Where did you get the direction?
The 30? Okay, so because the x is positive, right? So that's to the right, which is east. And positive 1.65 up, which is north, right? So it's east and then looking north 30 degrees. Anything else?
Whoa. Is it?
Made daily.
Is it made from real